All right, so what we're looking at today is projectile motion. So again, what we're doing is dealing with motion, but again in two dimensions. Now, last class we looked at started with motion and how we had to use vectors and breaking those vectors apart and putting them back together. Now that was for one specific type of question with two-dimensional motion. Today what we're going to look at is solving all the different types of two-dimensional problems. And so we have a situation here. A soccer ball is kicked at a velocity of 25 meters per second at an angle of 35 degrees to the ground. We want to find the maximum height. And so this is two-dimensional motion because we have a soccer ball here that's being kicked. All right, and it has a magnitude or a velocity of 25 meters per second. And the angle here is 35 degrees towards or with the ground. And I got my ground here in a green light. Now, when we are dealing with two-dimensional motion, which means that we're combining both left and right and up and down in this situation, where in our first unit, all we did was straight line. It was either straight up, straight down, or straight left, straight right, or straight forward, straight back, or north, south, east, west. You got the idea. Now, when we are dealing with two dimensions, we are again going to use our motion equations, but because we're in two dimensions, we're going to have two sets of them. And so what I mean by that is our x coordinates, or our x values, which again refers to our horizontal components, instead of having a v1 for an initial velocity, we're going to have a v1x. Just like vf, we'll have a vfx. And acceleration, instead of an a, well, we'll have a ax. And instead of a delta d, a displacement, we're talking about the displacement in terms of horizontally, we're going to call that delta x. All right, now we also do the same thing for our y's, which is our vertical components. And so instead of a v1x, we're going to have a v1y. We're also going to have a V2 or VF, VFY. Instead of an A or an AX, we're going to have a AY. And again, instead of our delta D, because we're talking about a vertical displacement, we have a delta Y. All right, now there is one variable because these all have direction, right? These all refer to the horizontal motion of our soccer ball in this case. These all refer to our vertical motion of our soccer ball. There is one variable that doesn't have, has nothing to do with either vertical or horizontal, and that's what I call the bridge. And that variable that I left out is our delta t, our time, which again doesn't have anything to do with horizontal or vertical. Now, we have our original situation here, and what I want to do is find the max height. Now, with our soccer ball launching here, what we can do is find the different vertical and horizontal components of our original velocity, which is something we've done before. So again, using trig, I could find the horizontal velocity, which would be our v1x, and I can also find my initial vertical component, which again would be our v1y. Now again, that's something that we did last class using trigonometry. So let's see, real quickly, I'm going to find those. So there's our 35-degree angle. My vertical component here, my v1y, is the opposite. And so, and I've got the hypotenuse. Again, you're always going to have the hypotenuse. And so v1y is going to equal 25 times, it's the opposite, sine 35 degrees. All right, so my v1y would equal, let me see here, punch my values in, I get 14.3, what else does it say, 4. All right, similarly, I'm going to find my initial horizontal velocity of my soccer ball, and it is adjacent to my 35-degree angle, and so I've got v1x is going to be the magnitude times cos 35 degrees. All right, and let's see, I'm going to sub that information in here. So let's see here, cos 35 times 25, I got 20.48. All right, so right just initially, given our information, I've got two of my variables. All right, so I'm going to plug those in. So again, my V1x is 20.48, and my V1y is 14.34. All right, now that's all I've got so far, but here's a couple of things. Acceleration in the x direction. Now, what that means is horizontally, is there anything pushing or stopping or speeding up this soccer ball? And we're dealing with a perfect world, isn't that great in physics, where there is no air and there's no friction or nothing like that going on in the air. And so the acceleration horizontally, there's nothing slowing the ball down or speeding it up horizontally. And so our acceleration is zero. Now in motion, when you have an acceleration of zero, that's a nice way of saying your velocity is not changing. Nothing's happening. And so if our V1x, our initial velocity, is 20.48, then our final velocity will be 20.48. All right, let's see here. What else? Delta x, yeah, I don't know how far this ball traveled. Delta t, I don't know how long it traveled. Let's see here. Oh, I've got my initial vertical velocity. So now I'm in my vertical components. Acceleration vertically. Is there something vertically that's either moving the ball up or down? And the answer is yes, gravity. And gravity accelerates downwards at a rate of 9.8 meters per second. And that's all the information that I know just starting out. So now I get to the question, what it's asking, all right, is find the maximum height. All right, so what we want here, height, again, is a vertical attribute, and we are looking for delta y. So I'm going to put A here because what we're doing today is just one example to start out. And so in part A, I've got a question mark. Now, here's the other thing is, what else do we know at the maximum height? That at the maximum height, we got our variables here. Now, here's something key. We had this before in one dimension, is that when you're talking about a maximum height, and if I just look at it as in terms of vertical, your item or your object or whatever it is moving at a certain velocity. And that velocity is decreasing as we go up. And then it gets to its maximum height. And that is, in fact, the one spot where the velocity is zero. So the entire time your thing is moving up, the velocity is positive because it's moving up, but it's getting smaller. So like 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. There's your maximum height. And then your velocity becomes negative. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, on the way down. And so when we are finding the maximum height, that means vertically, our final velocity is 0. All right, so it looks like I'm going to be working with my vertical components to solve this equation. Now, what I again need is my motion equation sheet here. All right, so I got that out again. And so now I'm matching up these formulas with my variables here. All right, so I'm looking for a delta y. That's the whole thing here, finding the maximum height, which on my formula sheet would be referred to as delta d, right? But we're looking at delta d vertically, which is called delta y. That may hopefully make sense to you. All right, so I'm looking for a formula with a delta d in it, or in this case, delta y. So I look at my first equation, and I'm doing the same method I did in Unit 1. And the first equation doesn't even have a delta d in it, so I can't use it. I got the second equation. It's got a delta d in it, but I need a vi. Okay, I've got my vi, or in this case, v1y. But I need delta t. All right, I don't have delta t. Let's see, third equation. I got a delta d, but again, there's missing a delta t. All right, I get to my fourth equation. It has a delta d. I need a vf, which I have. I need a vi, which I got. And I need an acceleration, which I got. Perfect. So it looks like I'm going to use my fourth equation. Now I'm going to rewrite this fourth equation so that it corresponds to the variables that I have now, or that I'm working with, or how I'm labeling them. All right, so for the fourth equation, instead of a VF squared, I'm going to write VFY squared, because I'm dealing with the Y components. Same thing with our initial velocity, where I got a V1 Y squared, plus 2, instead of an A, well, I'm just going to write a Y, and instead of a delta D, I'm going to write a delta Y. All right, so there's my formula. It's my fourth formula. I just rewrote it in terms of, again, just vertical components. All right, well, now it's time to substitute in. So let's see here. VFY is 0. So I'm going to have a 0 squared is equal to, let's see, I'm going to take my V1Y squared. So I got a 14.34 squared. All right, keep going here. I got a plus 2 times AY, which is a negative 9.8. Good old gravity there. And on the end there, I have my delta Y. All right, so let's just simplify things here. 0 squared is 0. 14.34 squared. Let's see here. I don't know what that is. 180 something, 90 something. Oh, 205.64. All right, and then I have 2 times negative 9.8 times delta Y. That's a negative 19.6 delta Y. All right, so again, just simplifying my equation, getting delta Y by itself. So I'm going to move this term over to the other side, the negative 19.6 delta Y. So when it changes sides, it changes sign. So we have 19.6 delta Y is equal to 205.64. All right, so the last thing I need to do here is divide by my numerical coefficient. And I get my max height. I take 205 divided by 0.64, or sorry, 205.64 divided by 19.16, and I get, let's see how good this kick was, 10.49. So this soccer ball went a maximum height of 10.49 meters. So I'm going to put that in here. I'm not sure if I'm going to need it again, but we'll throw it in there. So I've got my answer to A. All right, so there's our maximum height, but then we get to B. So again, a different scenario. And I'm going to erase these components because I don't need them anymore. I got them written down here. Give yourself some room there. We don't need the max height anymore. That's what we're looking for. All right, so then we get to B, which says, what are we looking for now? Find the time it takes for the ball to land on the ground. All right, so looking for the time it takes to land on the ground. So now I go back to my variables here. We're looking for time, so this I'm going to put this as B here. All right, so we're looking for time when it lands on the ground. So what other variable does that affect on the ground? The ground referring to, again, a vertical component. And when you're on the ground, I know the displacement or the distance is 0. Your height is 0. So my B here, now I've got a delta Y is 0. All right, and so now again, same scenario, but completely different question. So I'm back to my formula sheet here, where I am looking for, let's see here, delta T. All right, so let's see here. I look again at the first equation. I got a delta T in it, but I need an A. Okay, I got it. A VF. I don't know the VF when it's on the ground. That sucks. All right, let's see what else we got. We get to our second equation. Delta T is in it. Delta D, okay, is 0. Good. VI, got it. Acceleration, got it. Time's in there, got it. All right, so it looks like I'm going to use my second equation here. All right, so again, I'm going to rewrite it in terms of our components vertically. All right, so here we go. Instead of a delta D, I'm going to have a delta Y. All right, VI, well, that's V1Y times delta T. All right, plus 1/2 AY delta T squared. All right, so now I'm going to substitute into my equation here. So again, we're dealing with B, so the delta Y is 0. V1Y is 14.43. Oh, sorry, 14.34. Get my numbers wrong here. All right, now I've got the plus 1/2. Again, with a fraction, I always like to convert it to a decimal. So we'll just go with 0.5. AY, again, that's our gravity, which is negative 9.8. And I got times delta T squared. All right, again, just simplifying things here. So I got 14.34 times delta T. I take my half times negative 9.8 times the delta T squared. I'm going to have a negative 4.9 delta T squared. Now, here's something to watch out for. I have a delta T that I'm solving for here, right? But I also have a delta T squared, which means I have a quadratic equation on my hands. But I'm lucky in this case. I could use a quadratic formula. But in this case, because there's only 2 terms in the way it's set up, I can actually just factor out a delta T. So because that's common factoring is what I'm doing. So I factor out a delta T. And so, well, my first term here is going to be 14.34 minus 4.9 delta T squared. Now, again, this little grade 10 math is that when you factor, and it's called that zero product property, again, you always have to, when you're factoring, you always have to have a 0 on one side of the equation, which I did. I forgot to mention that. And then when you do factor, what you do is you set each piece equal to 0. Now, there's 2 pieces, believe it or not. And I should get rid of that square because I factored out one of them. There we go. All right, so there is 2 pieces. This is the first piece. And what you do is you make each piece equal to 0. So the first one's pretty simple. Delta T equals 0. Look what the question's asking. Well, I guess I didn't write it down, but the question's asking, find the time it takes the ball to land on the ground. Well, delta T equals 0. That's the starting time. Here's the time we're going to be looking for. So again, I'm going to make this piece equal to 0, where I take my 14.34 minus 4.9 delta T equals 0. All right, now I'm going to solve this one. So I'm going to take this negative 4.9 delta T over to the other side. So it becomes a positive 4.9 delta T. All right, and then I'm going to divide both sides by my numerical coefficient. And delta T is equal to whatever, 14.34 divided by 4.9 is. And I am getting, let me see here, 2.39 seconds. So this time we got 2 times. This one refers to the very start where the ball is on the ground. And this is where it lands. So it took 2.39 seconds for this ball to hit the ground. All right, let's see. So I'm going to erase this, and we'll get to C, part C. Oh, 2.3, what was that? 2.39 seconds. So I'm going to write that in, actually, because I found it. All right, so let's see here. B here, 2. What was it? 2.93 seconds. All right, there we go. All right, now again, we get to see how far horizontally does the ball travel? Horizontally. Looks like we're going up here now. So we want to know delta X. How far does this ball go when it lands? So here's our ball. Boom. How far does that travel? All right, so that is going to be our delta x. So I'm going to put a C here. We want to know that. Now, in C, how far does this ball travel? When it stops traveling, as we would say, it hits the ground again. So C is 0 down here. So B and C are the same thing, which means this time is also our C value, 2.93 seconds. All right, now looking at my formula sheet. So if I'm finding delta x's, so now I'm working with my horizontal components. But again, delta t can be used for either horizontal or vertical components, and that's why I call it the bridge, and that's why I put it in the middle. All right, so I'm looking at my formula sheet once again. We are looking for a delta x, which again is delta d on here, and this is all the stuff I got. So let's check out my first equation. It doesn't even have a delta d, no good. Second equation, delta d's got it in it. We need vi, which I do. I need delta t, which I have. I need my acceleration, which I do. And I need my time, which I do. All right, looks like the second equation again. All right, so here we go. Again, instead of a delta d for my second equation, it's the same equation I used last in part B, but instead of a delta d, I'm going to write delta x this time. Vi is going to be a v1x times a delta t plus, once again, a half, but instead of an a, I'm going to have an ax, and again, times delta t squared. All right, so there's my motion equation rewritten. All right, so I'm going to sub my values in here. Oh, the best part is we don't even have to isolate here. So we got delta x is equal to, let me see, v1x is 20.48. Delta t, 2.93 seconds before it hits the ground. All right, plus half again, convert that fraction to a decimal. My acceleration x, again, there was nothing moving this ball forward or stopping it from going, so it's 0. And times my time, which is 2.93 squared. All right, so we got delta x. Now, over in this term here, 0.5 times 0 is 0. So it doesn't even matter what that 2.93 squared is, because 0 is going to make this whole thing 0. And so my delta x, how far did this ball travel? I'm just going to take my 20.48 and times it by 2.93. And I get that this person kicked the ball 60.01 meters. That is a big kick. All right. So let's see. Now, we get to D. Now, D is a nice, interesting situation. Again, this is where some physics comes into play. Is that this soccer ball is being kicked on level ground. That is key here. Level ground. And so what we're looking for in D is finding the final velocity of the ball. Now, this is, again, a little physics, is that if you are on level ground, and your ball is launched at a 25 meters per second at a 35-degree angle, your object will strike the ground at 25 meters per second at a 35-degree angle. And so our VF is 25 meters per second, 35 degrees with the ground. And that's because, again, your horizontal velocity or acceleration, is 0. So that doesn't change anything left or right. Now, in terms of vertical, is that you're being decelerated or slowed down at a rate of negative 9.8 meters per second. But when you hit your max height, you get a velocity of 0. And then when you come back down, you are being accelerated at a rate of 9.8 meters per second squared. So your rate that you're being slowed down on the way up is the same as the rate as that you're being sped up on the way down. And that is why your velocities match. Your starting velocities and your end velocities match. Now, at 10:30 today, when we do part 2 and we do the second example of projectile motion, that is not going to be the case. And so we're going to look at how we find the final velocity if we are not on level ground. All right, so that is the start of our projectile motion, or part 1, I should say. Give me a second here.